So, hello guys, this is a relatively short video that I'm making today, and has nothing to do with games or whatever, but it's just something that I've been currently working on, and I thought you'd enjoy it. So, what this is basically, I have been working on a project, and I was required to work with a lot of random number generators, so I thought it would be an excellent opportunity to make one of my own. And this is based on how random numbers are usually generated in the game. So, I won't be going to how to generate a uniformly distributed set of random numbers, because there are a lot of videos and that requires a bit more thought into it. So basically these random numbers, they're not exactly random number generators, they're random number redistributors, so to speak. So for example, if you're playing a game and you have a shotgun and you have the pellets, how they spread away from the center where you aim, that is determined by a random number generator of a particular distribution, and it's not necessarily uniform, because otherwise it would look too unnatural to look at. So basically this is what it does. Now we're gonna consider the uniform distribution as a granted, so we're only generating uniformly distributed random numbers here, and what we're basically doing is we're redistributing them given a particular distribution. So generate an x and a y for this example, just so we can see a bit more. When we plot the scatters, they will be a bit more visible to us. So now I have these three distributions here. One is an exponential distribution, one is a bell curve, or no, this is not the Gaussian curve, for those who know what that is, because that has a bit of an issue when I come to explain how it actually functions. And an inverse square distribution. The inverse square distribution is actually a very handy tool to have, because many things like forces acting at a distance, like gravity, electromagnetism and such, usually drop off at an inverse square rate, which is 1 over x squared. The exponential distribution is e to the minus x, and the bell curve is the derivative of a sigmoid function, which I can't remember, but I probably put up on the screen. So, how does this work? Basically, when you generate a distribution, you get uniformly distributed random numbers. So now, if you take the distribution that you actually want, and you find the cumulative distribution function, which is for the probability that an object is between 0 and some value, it's generally the shape of an S, so it starts from 0 and then slowly climbs up to 1. You can find the inverse of that cumulative distribution function, and then put your uniformly generated random numbers through that inverse function to transform them into a set of random numbers generated with the distribution that you want. So I have some examples here. I'm taking this same set that I'm generating up here. I'm generating 5,000 random numbers. Actually, I'll leave it at 5,000. And then first I'm arranging them in a sort of bell curve. Well, this is not the actual bell curve, because for those of you who did statistics or maths, you know that the Gaussian curve has a tiny bit of a problem when it comes to the cumulative distribution function in terms of computability, and it's not very good analytically. So I'm using this as a sort of mock bell curve, and this code will plot it. I'm using Python, by the way. And then I'm running the exponential, and then the inverse square. So running this, we have this as our plot here. This is for the bell curve, like, so you know, you can see it's more of a shotgun type of spread. Granted, it's sort of a diamond shape here, so there's a little bit of more mathematics involved to make it circular rather than a diamond shape. Now this is the exponential distribution. So you can see you have a lot here, and then it slowly decays. The exponential distribution is usually used to distribute, like for example, how a radioactive material decays. So if you have something like, for example, in rust, I think it follows this kind of distribution where you have you build something and then it eventually sort of degrades. But I think that they run an actual analytic exponential function for that, but I'm not entirely sure. But if you want to do it with RNG, this is basically the function that you would use. And this, although not very fun to look at, is the inverse square. Mainly for these, look at along the axes, not what's in the middle. So you can see basically it's a lot here and it slowly decays. This is how a force would decay, sort of, like I mentioned before. So yeah, that's basically it. And the thing that I mentioned, I should probably emphasize a little bit, is why I told you to look on the axes. And to make these from a diamond-ish or a cross-like shape, you would not use X and Y and then plot them, because otherwise you have X and Y and zeros in the middle. But you would use just an R, which is a radius from the point that you are focusing on, and then you would set up a uniformly distributed angle and then plot using polar coordinates, so it would be a more spherical type shape, which I didn't bother going into here. So yeah, that's pretty much it. Thank you for watching.